Welcome back. This is section 7.1.1 central limit theorem. Very important and it will be slightly confusing, so I want you all to pay complete attention. So let's go ahead and read what the central limit theorem says. The central limit theorem states the fact that the distribution of a sample mean of population becomes closer to normal distribution as the sample size increases. The central limit theorem can also be abbreviated as CLT. Central limit theorem of mean says if you keep drawing larger and larger samples and calculate the means of those samples, the sample means will form their own normal distribution or a bell curve. What does that even mean? So let's start with what a central limit theorem says. Let me give you an example. If you're trying to calculate the height of human race, what is the sample that you will pick? 2? No. 3? No. 10? No. 50? So when I'm talking about population, it's impossible for you to calculate the height of every human being and then calculate the average, right? So you pick a sample. The question is, how large should your sample be? That's exactly when the central limit theorem plays a role. It says that the fact that the distribution of the sample mean of the population becomes closer to the normal distribution as the sample size increases. So technically what they're saying you is you need to take a larger sample size so the sample size gets closer and closer to a bell-shaped curve. Now let's take another step and talk about what central limit theorem of means mean. So before I do that, I'm going to go ahead and show you a stimulation here. So right now I have a bell-shaped curve. I can change this to a uniform curve. It's straight uniform, right? I can also change this to a right skewed. So it's right skewed. So what I'm going to show you is from each of this distribution, I am going to take a sample size. And I'm not just going to pick one sample. I'm going to take a sample, a sample, a sample, a sample, and a sample, and a sample. What am I going to do? I'm going to find the means of all these samples. And I'm going to prove to you that when I put all these means together, the means form a bell-shaped curve. So let's take a look. I'm going to start with the right skewed. I want you to focus on what this distribution is. It's a right skewed distribution. And I'm going to take a sample size of 15. I'm going to pick one so you can see what's happening. So I'm going to take 15 samples. 1, 2, 3, 4, all the way up to 15. There you go. 15 of the samples. So the first one is your sample data set. The second one is I'm picking the samples, and the third graph that you see right here is the mean. So according to your central limit theorem of means, if you take these samples multiple times and calculate the means form a bell-shaped curve. So let's go ahead and take a look. I'm going to take 5 times. That's still small. Let me take 1,000 of these samples and then calculate the means and graph all the means. So when I'm talking about the means, I want you to focus on the green color. Now I'm going to take thousands of these samples. 1, 2, 3, boom. You see what happened? It mimics a bell-shaped curve. Let me take it one more 1,000 times. Look, it's another bell-shaped curve. Now let's go ahead and take a uniform distribution. It's all straight. Again, I'm going to take a sample size of 25, let's say. I'm going to take it once. So I took one sample. Look at the green one. I have a mean. I don't want to take it once. I want to use the central limit theorem, take it multiple times. So let me take this 1,000 times. There you go. As soon as I click 1,000, the graph automatically becomes a bell-shaped curve. So it does not matter what graph you start with or what distribution you start with. When you take the samples multiple times and take the means of those samples, those means depict or mimic a bell-shaped curve. Okay, let me do it for a normal distribution. Taking a sample size of 15,000 times. So look at all the way in the bottom for the green color graph. Boom, a normal distribution. That's the magic of statistics. Now what am I focused on? Right now, you know that when you take the sample sizes multiple times, when you take a larger sample size multiple times and graph the means of those samples, it becomes a bell-shaped curve. What else should you know? The two things you should know is the mean and the standard deviation. What I want you to focus is look at the mean of the distribution. It's 25. The mean is 25 right here. You see 25 and the mean here is 25. So what I'm telling you is the mean of this distribution is same as the mean of this distribution. But look at the standard deviation. The standard deviation is 5 and the standard deviation is not 5. So there is a formula for that. Again, let me show you one more. Uniform distribution. What is happening? I'm taking a sample, right? 1,000 times, calculating the means of all those 1,000 samples, and I'm going to prove that the means of the mean is same as the mean of the population. 1, 2, 3, go, 1,000 times. Oh, I should have taken a larger sample size. 1,000. There you go. Now I have a sample size of 15, and now you see that it is a bell-shaped curve. Now let me take a larger sample size, larger than 15, 30, and then it's a perfect bell shape. So as I keep increasing the sample sizes and taking multiple samples, it gets closer and closer to a bell shape. Now focus on the mean of the population. The mean of the population is 25 right here. And look at the mean of this one, 24.9, so very close. So the mean of the population is same as the mean of the means, okay? Now let's go ahead and jump into the normal distribution. Sorry, the central limit theorem. So according to the central limit theorem, so the central limit theorem of mean states that the mean of the normal distribution of sample means is equal to the mean of the original distribution. What do I mean? I'm going to go back to the animation here. So the means of the samples, the means of the sample is equal to the mean of the distribution itself. So you see I have 25 right here and I have 25 right here. But what about the standard deviation? When I'm going to go back to this distribution, the standard deviation is 14. Is the standard deviation 14 here? No, it's not. It's 2.1. So that means there is a formula for standard deviation. So let's go ahead and take a look at that. So the mean is same. The mean of the distribution is same as the mean of the means, as we've seen that. Now for standard distribution, you have a formula. The central limit theorem of mean states that the standard distribution of the normal distribution of sample means is equal to the original standard deviation divided by the square root of the sample size. So that's what it means, square root of the sample size. So let's go ahead and jump into the first problem. It is very important that you all write this down. The mean is equal to, oops, wrong pen. So it's very important you understand, according to central limit theorem, the mean of the population is equal to the mean of the means, and the standard deviation of the population is equal to standard deviation of the sample divided by square root of n. Now once we know that, let's go ahead and jump into the problem. So here it says a college board estimated the mean SAT scores in 2016 as 1083 points with a standard deviation of 193. Assume the distribution of SAT scores is unknown and a sample classroom with a size n is equal to 30 was randomly drawn from the population of SAT takers. Using the central limit theorem of mean, what is the standard deviation for the sample mean distribution? Step 1, you need to go ahead and write down what information you have. So right now they say the mean SAT scores. So I do have my SAT score. Let me go ahead and expand this. So I do have the mean. The mean here is 1083, right? And I have the standard deviation. What's the standard deviation? 193. And I have a sample size. Sample size is 30. Right? What are they asking me? What is the standard deviation for the sample mean distribution? And according to the central limit theorem, the mean is same as the mean of the distribution, right? So here the mu is same as 1083. When they ask me for the mean, I don't have to do anything. As we have seen in the stimulation, the mean of the distribution is equal to the mean of the means. But when it comes to standard deviation, the standard deviation is equal to the standard deviation of the sample, which is 193 divided by square root of 30. So what I'm going to do is I'm going to go ahead and plug this into my class calc. When you are working with class calc, I highly recommend starting with the graphing calculator in class calc, because we're going to be doing a lot of probability distributions as well. So 193 divided by square root of 30. So my standard deviation is 35.24, rounding off to 2 decimal places. So it is 35.24. All right? All right, let's go ahead and take a look at the next problem. A cable company wants to study how many service representatives work more than 56 hours per week. Past data reveals that the hours worked for a service representative have a mean of 54. When I see something that is of my interest, I'm going to go ahead and highlight that with a standard deviation of 15 hours. The normal distribution for the population is shown. I did not put the graph in here, but it's shown a dotted black line. The company plans to take a random sample of 30 such employees and will calculate the mean hours worked for a sample to compare to the known hours worked. Compute the mean and standard deviation of the sampling distribution of sample means for a sample size of 30. Round your answer to the nearest tenth. Again, it's a sampling distribution, and we know that the mean of the sampling distribution is same as the mean of the original distribution or the sample distribution, and the standard deviation of the sampling distribution is equal to the standard deviation of the distribution divided by the square root of n. So let's go ahead and start with what we have. The mean is 54. The standard deviation, let me erase this. The standard deviation is 15, as I have it from right here, and the sample size is 30. So I know that the mean mu is same as the mean of the distribution, which is 54, right? And the standard deviation is simply the standard deviation divided by square root of 30. So when I go ahead and plug that in class calc, let me go ahead and plug it in. It is 15 divided by square root of 30. I get 2.74. So it's 2.74. So we found the mean of the sampling distribution, and we also found the standard deviation. What's my next step? What is the probability? Keep in mind, every time they ask the word probability is nothing but it's the area under the curve. So we know that this sampling distribution is nothing but it mimics a bell-shaped curve, and they're asking us to find the area under the curve. How come my curve changed like that? Okay. I know that the mean of this distribution is 54. And what are they asking me? What is the probability that the sample mean for a sample size of 30 will be more than 56? So this is, if this is 54, my 56 would be right here. More than 56 is to the right hand side. So I highly recommend you all drawing the graph so you can visually see what's happening and then calculate. Now let's go ahead and calculate it. So here I am. You always make sure you are in a graphing calculator. I'm gonna erase this one. When I'm trying to find the area under the curve, where do I go? Stats, distribution and plots, normal distribution. Remember, this is normal distribution with mean of 54 and standard deviation of 2.74. Right, that's what we have. So let me go ahead and plug that in. So I have mean of 54 and standard deviation of 2.74. So that is my normal distribution, but I'm trying to find the area under the curve, so I click on CDF. Remember from section 6.1, I'm guessing? And I'm trying to find area to the right hand side because it's 56, so I'm going to plug it on the left hand side, 56. As you can see, this is the area to the right. I want the area to the right. This is the probability, and that's exactly what I'm looking for. So what is my probability? 0.2327. So the probability here is probability that x is greater than 56 is 0.2327. And that is your final answer. Okay? Now let's go ahead and take a look at the next problem. This might get slightly confusing, but I want you to do it step by step as I am doing it. That way you will not make a mistake. Okay. A donut shop that specializes in unique donuts made from potatoes wants to learn more about their business costs. This is where statistics is used. It's used in everyday life. You need to know what's going to happen, how your future is going to be, what happened previously, so you can estimate and be prepared for it. The past data reveals that the cost of 50 pounds of potatoes has a mean of 75. Remember, as soon as I see something that interests me, I will highlight it with a standard deviation of 13. So the average for 50 pounds of potatoes is 75. Standard deviation is 13, and it's normally distributed. The donut shop plans to take a random sample of 31 such 50-pound bags. So one sample, another bag, another bag, another bag. So 31 of these. And will calculate the mean cost of the sample to compare to the known cost. Compute the mean and standard deviation of sampling distribution, right, of the sample means of the sample size 31. Very good. So I know my sample size is 31. I know my standard deviation is 13. I know my mean is 75. And according to central limit theorem, the mean of the sampling distribution is same as the mean of the sample, which is 75. The standard deviation is using this formula, standard deviation divided by square root of n, which is 31. And what is that going to be? I don't know. I got to plug it in class calc. Okay, so I'm going to clear this. And 13 divided by square root of 31. So my standard deviation is 2.33. Standard deviation is 2.33. Now that is not what they asked me. There is one more step to it. And what is that? They say, what is the probability that the sample mean of the sample size 31 will be greater than 76? So they're asking, what's the probability that the sample mean of this 31 will be greater than 76? So what does that mean? The cost is greater than $75, which is my average. So what do you think is the probability? I don't know. Every time they say probability, I know it's the area under the curve. Hopefully this curve comes properly. There you go. I know that my mean is 75, and I'm looking for probability that will be more than 76. So this is my 75, so this is my 76. More than is always to the right hand side. And again, this probability is nothing but your area under the curve, right? Again, what is your mean? Your mean is 75. Your standard deviation is 2.33. We have calculated that. You will simply go ahead and plug this into your class calc. Alright, let me go ahead and pull up your class calc. Where do you go? Stats. Every time you're looking for probability, what do? Stats, distribution and plots, normal distribution. Once I get to the normal distribution, what is my mean? My mean is 75 because you know that's what it's given. What's my standard deviation? You calculated that, 2.33. What are they asking me? Where is my curve? There you go. That's my curve. If you don't see the curve, click on that little wiggly thingy. That the curve is going to come up. And I want to find the cumulative distribution. So I'm going to go ahead and click CDF. And I'm looking for area to the right hand side. So I know I have to plug it on the left hand. 76 right here. Let's just say you did not know which side to plug it in. So instead of on the left hand side, if I plugged it on the right hand side, you see, that's not what I want. I want area more than 76. So you know you have to go back and change it. That's why I always ask you all to graph it out so you all can literally see. This is area to the right, area to the right. So boom, you have the right answer. What's my probability? Probability, oops, I should have looked at that. My probability is 0.333. Probability is 0.333. And that's the probability, the final answer. All right, now let's go ahead and take a look at the other one. Okay, suppose heights of seasonal pipe saplings have an unknown distribution. So looking at heights of pipe saplings have an unknown distribution, so they don't know what the distribution is. But keep in mind, it doesn't matter what distribution it is. When I do sampling distribution, automatically becomes a normal curve. So I have a mean. Every time I have something of my use, I highlight it. Standard deviation, highlight it. I have a sample size of 55, highlight it. And again, I know what central limit theorem is. It doesn't matter what distribution you give me. According to central limit theorem, my mean here is 291. Standard deviation is 14. Sample size is 55. And according to CTL, the mean of the sampling distribution is same as the mean of the sample. The standard deviation of the sampling distribution is the standard deviation of the sample divided by square root of 55. And that is, I don't know, I gotta plug it in. Clear this. It is 14 divided by square root of 55, which is 1.8. I'm going to round it off to 2 decimal places, 1.89. So this is 1.89 is your standard deviation of sampling distribution. All right, let's go ahead and take a look at the next problem. The length of text messages have an unknown distribution. Again, doesn't matter what the distribution is. When I do sampling, I know it's going to be a normal. With the mean of, again, when I see something of my interest, I will highlight it. Mean of 28. Standard deviation of 4 characters. So the text messages have a mean of 28. So usually you type 28 characters. And the standard deviation is 4. So I could go 4 below, I could go 4 above. And a sample size of 47 was randomly drawn. So 47 different text messages have been sampled. And they say, according to central limit theorem, what is the mean of the sample mean of the distribution? So I know the mean here is 28. Standard deviation is 4. And sample size is 47. So according to central limit theorem, the mean is same as the mean of the sample, and the standard deviation is standard deviation of the sample divided by square root of 47. Again, I'm going to go ahead and click on my class calc, delete the previous one. That's a good practice to always delete the previous ones. That way you don't have wrong numbers plugged in. So my standard deviation is 0.583. I'm going to round off to 2 decimal places. So 0.58 is my standard deviation. Again, keep in mind, it doesn't matter what distribution you take. When you use your central limit theorem, the sampling distribution kind of mimics the standard or the bell-shaped curve.